Hello everyone. I hope everybody's doing good. Apologies for the problems with the stream, but I think now we're finally live. Can I get some hello in the chat if you can hear me well? Everything seems good. Hello, hello, hello. Yes, okay. And there you go. That is a pretty quick, pretty short delay, so that's not too bad at the end of the day. This is actually relatively nicer than YouTube in terms of the delay. Hello, hello, hello. Okay, cool. So how many people do we have in here? Can you guys see that? I don't know if I can actually see that. I've never done this the Twitch thing, so I'm not 100% sure. We have 30 people. Oof, that's pretty low. That's about a third of the class, you know. So it is what it is. Hopefully they catch up. 19 views. What does that mean? Well, okay. Well, either way, what's gonna happen is I set it so that it stores it on Twitch as a replay, but they get deleted after 14 days. But either way, I'm recording the stream, and so I will upload that recording when I finish to YouTube, once YouTube is friendly with me. I don't know what's happening with that, but it's good now that we have a backup as well. So that's good on that side. So anyways, we started at 9:30, so we'll kind of go until like 10:45ish, and then we'll do the office hours afterwards. But okay, so all right, good. You guys, because yeah, I don't know what I'm looking at, so you guys keep track of how many viewers we have, because I have no way of checking that. So cool. All right then. So let's hop right into it. Okay, so here we have the little iPad, and everything is smooth. Okay, that's a good sign. So you should be able to from your end. Yeah, but the thing is, I don't know the. I mean, okay. Oh, okay. Here we go. Yeah, 30 viewers. It's just it's tricky to get to see that without, because I have multiple monitors, but I want to keep the chat at the same spot. So I'll have to fiddle with it later. This was kind of impromptu, which I'm not a fan of, but you know, I got it running, so that's good. Okay. So I went ahead and created a little to-do list of things that we're going to be talking about. So we are going to be talking about heapifying. So we're talking about heaps, and we're going to finish talking about that. We'll do an example with a max heap. We will talk about priority queues, which is an application of heaps. And then the homework is not done yet, but I want to introduce it right now on video. And that way, once I post it later, then you guys know what's up with that. And then if we have time afterwards, we can talk about tries. And I also do want to talk about AVL delete, because that's something we never talked about. I mean, it's relatively straightforward, but in fact, we'll probably start with that. But yeah, we'll mention that. And I also want to talk about, because a question that was brought up during the last video about stability of Heaposrt. So Heaposrt is not stable, but I'm going to show you something that I found that talks about stability in sorting algorithms. And yeah, so that's our little schedule of what we're going to do. So right now we are still at 36 viewers. Okay, cool. I don't have a Twitch account, but I can see and hear you. That's fine. I saw that message on Discord. You can also ask me questions on Discord, and that's fine. You don't need to have a Twitch account. Just have a Discord account. So if you guys are watching and you don't have Twitch, you don't have to make an account. You can just ask a question on Discord, and I'll check up on Discord. You can also join the voice chat and listen to me there. However, which I see one person is there. However, because of the audio being, even though it's short delay, but it's still a delay, you probably want to mute me on Discord so that you don't hear me twice out of sync. So that's what I recommend, and then just listen to the stream video. So that's my recommendation on that. So okay, so let's start with the AVL stuff then. So let me just go ahead and draw a little tree here that is an Avl tree, and so that's a binary search tree that is valence, log, and height. Nine, and then maybe like 12, 18, 17, and 21. And so is this balanced? Let's just check real fast. This should be balanced, but you never know. 2, 1, 3, 1, 1, 2. Perfect. We are balanced indeed. And so suppose that I want to delete something. So regardless of whether it is a binary search tree, that it's AVL, or just a regular, it could be a degenerate tree, whatever it is, the trick to deleting a node, and I'll write it here, and again, these nodes are on the 1002 section, so you can get them from there. So deleting nodes, you always take the predecessor node in the in-order traversal, meaning that suppose that we're going to delete 12. Okay, that's the one we're going to delete. So how do we find 12? First of all, well, we say delete 12. So like suppose in the test I say delete 12. The process you have to do is you start at the root and you got to first find if 12 is even in your tree. So you check with the root, which is 10, and you say is 12 less than, equal, or greater than 10? And it's greater than, so you go this way. From there, you check 15. And so 15 is less than 12. Therefore, you have to go to the left of that. And finally, you get to 12. Suppose that you were looking for 13. What would happen is you get to 12 and you'd be like 13 is bigger than 12, and you go this way, but because it's null, you'd stop and say it's not found, can't delete something that's not there. But anyways, that's not the case here. Here we're trying to delete actually a number that is found, 12. At that point, you need to get the in-order traversal's predecessor. So what's the in-order traversal of this? The in-order traversal of this would be as follows. Let's just get rid of this color. We'd start here at 10. And then we would go to the 8, and then we will go to the 1, and then we would print the 1 out. And from there, we would go to the 8 and print the 8 out. So it'd be 1, 8. Or here, I guess I'll use this so you can see it better. 1, 8. This should be all review, but it's good review. From there, we go to the 9, and we print out the 9 because nothing there. So get that 9 in there. And from there, we go to the 10 and print the 10 out. So I'll just put it down here. And then from there, we go to the 15. But before we print the 15, we got to go left, right? Because in order is left, print, right. So left to the 12. And so we have found the 12. That's what we're looking for, right? And no, this is not how you initially find it. You initially find it just by going from the root as I did before. This is strictly for finding what to replace 12 with. So in this case, it happens to be that the predecessor of the in-order traversal is going to be 10. Okay? So that's what you would want to replace 10 with. Or sorry, that's what you want to replace 12 with. Okay? However, you don't always have to replace it with that. Here's the reason why. The only times that you need to replace it with something is if it has children. If it has no children, as is the case of 12, that's no problem, because all you have to do in that case is you can just simply delete it. And that's okay. However, if 12 had some children, that's when you would have to be like, okay, I need to actually go in and replace it with the children. So how would that look like? Well, suppose that there was an 11 in here. So now as you compute the weights, it goes like that. In this case, the predecessor in the in-order traversal, you go 1, 8, 9, 10, and you get to the 15, but you don't print that. You go to the 12, you don't print that. So it's actually the 11. So in this case, this is what you would replace the 12 with, which makes sense if you think about it. If we delete this part of the tree, then you just kind of hook that up and you're good to go, right? I'm just looking at the chat, see if there's anything, but nothing new. Okay, yeah, so how are we feeling on that? Does that make sense? Yes, okay, cool. Yes, sir. All right, cool. Okay, perfect. So so in reality, what is always going to end up being is you're never going to end up replacing something above the tree, like the 10. Like the 10 would never really go down. What ends up happening is more than likely, because the only times you're replacing things when they have children. So for example, if we need to replace 18, that needs to be replaced with something. If we need to delete 21 or 17, that doesn't matter because they have no children. The hardest one to fix is this one, the 10. That's the nasty one. If that's the case, it's still one of the children that you're kind of replacing it with. In this case, it would be the 9 because the 9 goes before the 10 in the in-order traversal. So let's go ahead and do that. Pick a number that actually creates something interesting. Because as you see here, if we delete the 10 with the 12, nothing happens. So let's say we just deleted, let's say we delete the 12. Okay? So in this case, we don't need to replace it with anything. However, we do need to recompute the weights going up from that spot that we deleted. So we don't need to recompute anything per se beneath it because again, it has no children unless you've replaced it with something. And even then it's okay. But upwards, you need to replace it. We have a question. So basically, if I had to delete or replace, it's hard to delete or replace if they have children, you will have to rotate. If I'm getting what you're asking and you could rephrase it, you're saying, if I have to replace something, I always have to rotate. Not necessarily, because like, for example, if we had something like this in here, and I delete the 12, and then of course it gets replaced with the 11, there's no rotations needed. So you can't assume that you have to replace, that you have to rotate after you've done the deletion, whether it's being replaced or not. It could also happen that it has no children. So like suppose we have the following tree. And then let's see, it could be a leaf node. So 1. Doesn't matter what these values are. Suppose they're like 1.5 or something like that. And so in this case, in fact here, so we got to pick bigger numbers so that I have options here. So 8, 10, 12, and then maybe like 7, and then 6. Yeah, okay, so in this case, this tree is balanced as it is right now, I believe. Well, not really, but if we have to put something on this side. But we can take care of that. There we go. So that tree's balanced right there. However, look at what happens if I delete the 12. I'm not replacing it with anything because there's no children, but it is making my tree unbalanced. So it is so there's times when deleting a node that has no children will unbalance the tree and you have to rotate, and there's times when it won't. And there's also times when you delete a node and you replace it with something else because it has children, so you're probably one of the children, but you do have to rotate. So you can't make an assumption either way. And you're saying, I meant like if they have children, the node that we're replacing is harder to delete or replace them. No, like I said, it can be either way. Here are examples of where I deleted something where it had no children, but I still now have to rotate, and we can fix that, and we can do this in a second. And then we also have the other example, this one. Can you see the mouse? Why can't you see the mouse? There we go. This one, where when we delete that, we don't have to rotate anything. So there's no surefire where. RN6 and 7 is supposed to be on the left. Yeah, that's true. It's okay. We can make them 9 and 8.5. There we go. Thank you. Good catch. But yeah. So anyways, we will do that example right now. We'll leave it because now that we came up with that example, it's actually pretty good. In fact, just to make it nicer so we don't have nasty decimals, let's just pick bigger number here. And then we can make that 42. Okay, that's good. Perfect. So first, let's do this example though. So in this example, the way we have it set up, that's the current weights, right? So we're going to go in and we're going to delete the 12. It doesn't need to be replaced with anything because it has no children. And again, the shortcut for that, even though it's the in order predecessor, blah, 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 is to pick of the left children. If so, okay. And maybe I should write this. the shortcut. So this is not algorithmic, but like test shortcut, for example, if you're doing this in a test. If you have a node, and you know this is coming from, whether it's coming from there or coming from there, doesn't matter. So if something's above this tree, but we don't care. If we're deleting this node right here, what we want to replace it with is, if there's a left child, go in that direction and then find the rightmost node possible. The rightmost node. Then you replace it with that. That's one case. Other case, there's no left childs. If there is no left child, then all you have to do is just bring up the parent. Or sorry, bring up the child to become the new parent. So that's like if we have something like this, then and you're deleting this one, then all you do is that, which is essentially what we did. Just connect those. So that's one solution. And similarly, if you have something like this, and you delete this, then you just connect it and you're good. So it's only tricky when you have two children. Which one do you pick? And you always go to the left side if you have the choice. If you have two children. And from there, of course, if this has no children, then bam, you just replace it with that. Problem solved. But, you know, more than likely, there's going to be more children down here. In that case, you go all the way to the right that you can. So like as far right as you can. So like if there's nodes over here, you know, then you don't go this way because that's not right. That would be going left. You go as right as you can, and this is going to be the in order predecessor always. If you're not comfortable doing that, you can just do your in order traversal basically. I have no idea what I said before. May you please repeat the first one. So we pick left and right most of left side. By the way, for the buffering video issue, you could try lowering the resolution and it might help. Otherwise, you could also pause the video for a second, which would put a bigger delay on your video, but then at least you would have less buffering problems. That's the reason it's buffering, is because there's such a short delay that it's just like pushing data fast. At least that's what I think is happening. So anyways, I'll repeat it though in case you didn't, because you guys are saying you might have lost some of that information. And that is when you're trying to replace a node, such as like 18, you are either gonna, if it's only one child, then that's easy. Just replace it with a child and you're good to go. It's only hard when there's two children, left and right. In that case, you always go to the left. And then if the left child has no children beneath it, then you just take that left child and you make it the new parent. So that means take the 17 and make it the parent. So if we were to delete 18 from this, all we got to do is replace that with 17. So it becomes 15, 17, and 21. And remember, this is a binary search tree. So like in a test, even if you have no idea what's happening, it's a binary search tree. So if you perform a rotation and like that breaks, like all of a sudden you don't have a binary search tree, so you have like something like 21, and then there's like an 8 here, then you're like, oh snap, something broke. That's when you're like, okay, I should stop. So there's also that sort of checking that you can sort of do to make sure you didn't break it. That's also good in your AVL assignment. If you do your Avl tree and you do a rotation and you print the rotation afterwards, and you see that something is not the order that it should be, it's out of the order, then you know you probably messed up the rotation. But anyways, back to this. As I'm saying, when you remove the parent and there's two children left and right, you go to the left if you have that choice. If that has no children, you pick that. If that has children, then you go to the right and you keep going as right as you can until there's no more right you can go. And if you have something of this form where it's like that, and then it goes this way, and then it goes this way, you're going as right as you can, which is this. You can't go further right. I know there's stuff right here, but that means going left first. You're going as right as you can, always to the right. So this way. It's mirrored for me, so you go this way. So we picked the left and rightmost of the left side. Yes, that's right. Very right. In theory, if this is all you have, then this is the rightmost. If it's only one child, if there's no children beneath that. So that's pretty much it. That's what you do. You do that replacement, and then you balance the tree. You balance from that node that you replaced upwards. You check upwards. So you first check here. In this case, this became a 0. It's unbalanced. At that point, you have to do your rotations. So in this case, it's going to be, I believe it's a double rotation, but I'm not 100% sure. So we will do the single rotation first to find out. So let's go ahead and try that. Heavy on time. We're good. Worst case scenario, we go a little bit over. I'd rather get you guys, because AVL is the hardest subject, I still think. And on test, people always mess this up. And I know that you have the online, and there's even like websites that can do the rotations for you, but I will know if you do that, because your rotations will be different than the way that I'm doing them. So it'd be like suspicious. So anyways, let's go ahead and just erase this so it doesn't distract us. We'll do that one in a second too, because that's actually a nice example too. So let's try to do that rotation this way. So I guess it's a left rotation because it's right heavy. So and then the 17 gets moved over here. Yep. Yeah, so it's oh. That's okay. That worked actually. Yeah, that worked. We're fine then. We don't need to rotate again, I think. So we're good. And then from there, here we can replace that here. I thought we'd have to do a double rotation, but we didn't. Here, we'll just put it like that. And we're good. Nothing else needs to be done there. So there you go. There's an example where it's not clear which rotation you have to do. Here's a good question. So since the test will be online, how do you plan on having us draw things? That's $1 million question. So one of the things that I was thinking of, there's two ways that we can handle that. One of them is the questions that involve drawing, which are going to be the building tree ones. You could do it on a piece of paper and then take a picture with your phone or scanner and then submit it online, and it's a time submission, so you have like 2 hours to do it or something for that section of the test, and then that's good to go. You could also use Paint on your computer or any sort of drawing tablet, anything you can. In fact, you don't even, that's probably better. You don't even need to print it. You could just paint. It'll be slow. So that's one way to do it. The other option is I can always make it like a multiple choice thing and draw the diagrams and make you pick which one is the right one. But that's I don't think that's ideal. So I'm not too confident on that. That's a lot of work for me too, actually, doing all those drawings and getting it. So, however, I'm going to see if there's a way that you can directly draw on Canvas quizzes, and that's why later on this week or next week, probably next week, I'm going to have an online quiz. It'll be like a 5.6 credit or something, and then you will be taking a AVL question actually that you will do, and it'll be good practice for you guys, and it'll also be good because then you can test to see if you have a way of submitting that sort of question, and that's the biggest thing that I want to know. So even though it's extra credit, you should all do that, because then you have no excuse during the test like, oh, my phone doesn't have a way of taking a picture or something. I'm like, well, you would have found that out if you took the quiz. So we'll have a lot of ways of doing it. So it'll be like a proof of concept, that quiz. The picture thing I think is ideal, but I really, really hope there's a way on Canvas that you can draw directly, because that saves everybody a lot of work. And no, I'm not concerned about looking at drawings because I don't do that. The TAs would, so that's okay. I'm sure they're having a fun time, so they wouldn't be sad about looking at pictures. So yeah. So what if you want to replace 10 from the very top? You would replace it with 9. Let's do that, actually. Let's say we delete 10. Usually deleting the root is the hardest thing because weird things can happen. So delete 10. Gets replaced with the predecessor, which is 9. And then you have to balance everything beneath it, potentially. You have to balance from the spot that you replaced from. So because you modify this section here, you have to work your way up from there to see if it's still balanced until you get here. So in this case, it is not balanced. Oh no, sorry, it is balanced. Yeah, we're balanced. We're good. So yeah, that's that. So okay, where's the other example that we had? So this one, we wanted to delete 13, I think. Yeah, that one was easy actually. Yeah, right. A little bigger. Will we be getting another worksheet for practice review? Yeah, I think we will. I think that's going to be the best thing to do, is to do another worksheet, because it'll be a good review for you guys. So you will get a worksheet and then you'll figure that out. The next test, I believe, check Canvas, but I believe it's 2 weeks from now. So next week we'll talk about hashing, and then we'll have the test. But we can always fiddle with the schedule of the test, and if necessary, push it further. I think my dog is triggered that you guys are taking a test. Padme! Shh. Okay. So yeah. All right. So push it further while we adjust. It might be a thing that we push it a week. I will announce it as we get closer. I think that's going to really depend on once we do the AVL quiz to test the technicality of that. So if it's a possibility. We also have to coordinate the timing because of the test. Because ideally, I want it to be limited time release, like of 3 hours for you to do the test. So we got to make sure that everybody can do it at that time. So I'll set up a Canvas poll, and we can set it up to do it in the afternoons or something, or whenever we know for sure people have that time slot. Because what I don't want is to have the test be like, okay, you have a full day to do the test. You have 3 hours, but you can do it anytime during the day. Because what's going to happen then is someone's going to take it first, and then they're going to leak the information to everybody else. Good. Here we have a question. So deleting a tree takes O(n) time because you have to find the node to replace the deleted node. Yeah, potentially. There are some shortcuts to this, because technically the in-order traversal only really needs to be performed on the children. So be like that. So really, I would say if you code this right, you can find the predecessor in half n divided by 2, which is still n, but just saying it's a little bit better. So but yeah, in a simple solution, yes, O(n) time, because you got to get the traversal in there. Can we have more examples of the replacement, please? Well, we're about to do it on this one here. So, vote. Which number would you like me to remove from here? I was thinking of removing 13, because that's actually that will make nothing. Because let's do 13. What's going to happen then? It gets replaced by 12. But then nothing interesting happened there. So vote. Yeah, it just gets replaced by that. Let me put more numbers in here. 55. 0. Let's see if that broke it. What about 1 and 6? Oh, okay, here. Sure. We'll do 1 and 6. Let's delete. Doesn't matter which one we delete, but let's say we delete 1 first. Of course, then nothing really happens. But then we delete 6. That's when things get a little bit more interesting. Because now, when we delete that, we're checking, we're checking our weights going up to the root, and we find that 8 is no longer balanced, right? We have a right heavy tree, so we got to perform a left rotation. So again, we start with the simple one. We start with the simple left rotation, and if that fails, we will do the double rotation. So let's go ahead and do the left rotation. That means, if you remember a little algorithm like that, and then we have 1, 2, 3, 4 for the children, and so it becomes 1, 2, 3, 4. That's on the notes. And so what ends up happening is 13, 8, 42. Oh, we have some questions as well. I'll get to you guys in a second. And then we gotta fix the children. So 5. And then there's no child there. oh, 2 gets here, so technically 12 gets here, and 11 goes down here, and that's it. Yep. Okay, so let's verify, which I already see it, but let's just verify. 1, 1, 2, 3. As you can see, it didn't fix it. It's still unbalanced, so we're gonna have to perform a double rotation. However, let's do something we haven't done yet. Instead of rotating back to the original shape, let's just take this one right here and do a double rotation on that one. And we can save a step. This is good in the test too. But before that, let's see what the questions are. If you append some number on the right of 12, then what would happen if you delete 13? So on the right of 12, so like 12.5, then you would replace 13 with 12.5 because that's the rightmost, right, of the left child's. So that actually would be an easy solution. You just replace that with that, and then it would still be balanced actually. So yes. On Discord, we have some questions. If we use Microsoft Paint to submit the drawings for the test, would you prefer it to be a PNG or JPEG file? Doesn't matter, but I suppose JPEG, because it's a smaller file. And it's, I don't know, when the T is downloading like 100 of these, it could make a difference in the download time. So, okay. All right, so let's perform that double rotation then. So which rotation are we doing? We're doing this one. So if we want to remember what the algo for that is like, is going to be don't worry that the letters look backwards like that. You know, I guess if you really want to put them that way, we can. Some people get triggered at this. So. Then that becomes Z, Y, X. And then from there, we do Y, Z, like that. And then for children, we'll do them a different color. We have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. You should know these by heart. Okay, so in this case, we have this thing. So let's just. Oh. We are on time. We're good. Okay, so we are going to take basically the this one right here, and we're gonna swap it into 12 here and 18 there. That's that first rotation. And of course, children are going to get moved around because of that. So if you want to, I mean, you can look at the algorithm, but also you can just imagine that there is the other imaginary node here. That's 8. That is 8. I don't know what happened with that. So I had it right the first time. Yeah. My bad. So anyways, if you want to make mistakes like that, that's when you add that imaginary node. So now that we have that imaginary node there, it's a little bit easier to see the rotation happening. Right? We can see it easier to become that way. That's why I like adding that node. And then your children. Every time you do a rotation, one children gets moved around. In this case, that children is 11. And this, you'll see, would match this up here. Okay, now that we've done that, you can get rid of our imaginary node. And now we can perform the main rotation per se to take care of this issue, right? So that is the second rotation there. So that means, if here, I'll highlight it for you guys. That's what we're rotating right now. That's our XYZ. And then get your children in place. 5 and 11 are still the same. And 13 is actually some. So in this case, actually, no children were moved. The children that would have been moved would have been this one here. So like if we had a 12.5, then that would have ended up here. But that's not the case here. Anyways, check the height of the tree. Balanced. We're good. Okay, any more questions before we go back to heaps then? Bruh, I thought the stream was delayed until 10 and I come back to find I got charged again. Feels bad, but you know, I didn't want, some people have class at 10, so I wanted to at least them to get a little bit of the stream. And yeah, we haven't talked about heaps yet, so you can always watch the beginning of the stream again with the Avl trees and you'll be fine. Now we're going to start talking about heaps, and it is 10, so that kind of worked out. Okay, so no more questions, cool. Back to our list of things to do. We talked about Avl tree delete. In general, this is just in general binary tree deleting. We talked about that. Now, before I talk about Heapify, I want to talk about the stability question thing that came up. So if I go and show you something, now I'm going to switch to showing you the browser here. Okay, so this is Geeks for Geeks, stability and sorting algorithms. And I recommend that you check this out. I can even post the link on chat. And so this should be a little bit obvious, but if not, that's okay. That's why I'm talking about it. If it was that obvious, then of course I wouldn't even talk about it, I suppose. So Heaposrt is not stable. Just like Quicksort is not stable. Just like it's pretty easy to mess up most algorithms to make them unstable. But there's also a way that you can make any algorithm stable. And the way you do that is you change what you're using for your compare function. So suppose that you're trying to sort using Quicksort a list of numbers. So for example, well, here, let's look at these numbers, I guess. The 10, 20, 10, 30, and 10. Okay? Of course, there's duplicates. And when you're sorting with something like Quicksort, which is unstable, when you're sorting something like this list with duplicates, they can get out of order. As you can see there. The way that they're signifying the different list of the different ordering is that they're using the colors. So you can see here that in this case, no, in this case, everything is okay. In this case, nothing got mixed around. But if you had sorted and this orange one or pink or whatever that is came after the green one, then it would have been out of order, right? So what we want is we want to be able to sort them and keep stability, such as that example is doing, okay? So one thing that we can do to make it stable is to add more than just what we're comparing. So for example, let me switch back to the iPad. Suppose that we're sorting the following list: 5, 8, 5, 10. Okay? And my sorting algorithm, we're going to call this 5A and 5B. Or even better yet, let's use the index to identify these 5s. So my sorting algorithm runs through this sort. And it turns out that the algorithm sorts it like this. And the numbers on the top represent what they used to be, like what what the old index used to be of where they were. And let's say the new index is, of course, in the bottom. So then it's very easy to identify whether the objects got sorted in a stable manner or not. Another algorithm sorts them like this. In that one, you know that it's unstable, right? Because the 5s got swapped. Now, in this case, stability doesn't matter because you're sorting as an integer. But suppose that these are objects and they contain other things that are not unique. So they contain their ships, for example, and you're sorting and you want them to have that original order, and there's a way to identify one from the other. Well, here's a trick that you can do to preserve stability in an unstable algorithm. Just like I'm doing here, I'm identifying the different 5s by having an index of their original order. I said 5-0 and 5-2. That's the trick. That's all you have to do to maintain stability, is to the key that you're using to sort, so the numbers themselves, don't just sort based on that key, which is in this case the numbers. Also, before you start sorting, create a secondary key that is just the order of the numbers in the original list, such as the most convenient being the index that you have to store them in. And so now, if this is an object, your object is going to contain 2 integers. One of them being the actual integer you're sorting, and the other one is the original ordering of the list. And then when you sort, you're not just sorting based on the numbers that you're working with, but you're also sorting based on the integers. And that way, you can differentiate here between which one should go first. And voila, you have preserved stability. If you think back to 202 days, if you took it with me, when we were sorting assignment 1, the bigrams, we sorted bubble sort twice because it was stable. But had bubble sort not been stable, and we wanted to still be able to sort them correctly, all we had to do is sort based on the first word and then the second word. Same thing here. We're just adding another constraint to sort by, and that will take care of making it stable. How does that feel? It's a little bit, now you're like, oh, okay, well, that makes sense, duh. I mean, it makes it harder, because now you're sorting based on 2 keys versus 1. But the amount of extra comparisons that you have to do is not too bad, because you only have to worry about that with duplicates. That's right. Very good. That's a good summary of what you're saying. Is you have to sort. So in the case that you're sorting the list and you find 2 items that are equal, the way you pick which one goes first is you base it on the old index. Now, let's think about time complexity for a second. How long is that going to take? Well, you sort the list. You end up with either of these first. One way of doing it is you end up with either of these, and then you just, for all duplicates, you make one additional pass and you sort the duplicate lists. So how long would that take? Well, at a simple glance, you might be like, oh, it's just one extra end pass. But not quite, because suppose that all of them are duplicates. So potentially that's a sort of its own. So you can use any sort you want for that, I suppose. But yet again, you'd have to be a stable sort, right? Otherwise, things would break down. So in that case, why are you doing this in the first place? So really, if we're dealing this with an unstable sorting algorithm, you don't want to wait until this step to do the sorting. You want to do it when you're sorting the original list by comparing both keys. So your first compare. So if you're sorting this list, like let's say you're doing it with bubble sort, okay? Even though bubble sort is stable, you could do this. You check 5 and 8. 5 is less than 8. You're okay. You check 5 and 5. Or sorry, suppose you're using insertion sort, I suppose, in that case or something. In this case, because they're equal, you look at the indices and then decide if you need to swap them or not. That kind of thing. So an example is actually, that's a good point. With the system name, if they're the same, then you compare the system ID. Exactly. So now, you can, using something like quick sort, you can still sort them correctly by using the ID. So actually, even though I hadn't talked about this concept, you had been using it already if you did it that way with assignment, what was it, 5? When you did all the sorting algorithms. So yeah, this is just something that I thought I'd bring up to reinforce something that you probably already knew, but you know, it could be a tricky question somebody could ask you, like in an interview, like, so how do you turn this algorithm into a stable sorting algorithm? How do you turn quicksort into a stable sorting algorithm? And then you can be like, well, when you're sorting, don't just sort by the key value, also sort by the index value along with the key value. So that way when you hit a duplicate, you can look at the old indices and sort based on that. And voila, now you've made quicksort stable. Not for free. There's a little cost involved, but the cost is pretty negligible. It's more of a space cost and things like that. Yep. And you see, yeah, some people did it that way. So in fact, if you didn't do it that way, you were inadvertently sort of doing it, even not being aware of it, because otherwise you wouldn't have made that work if you were comparing two keys. So, okay, that's that out of the way. So let's see other questions. Nothing so far. So back to this. So we took care of that, and we took care of that. So now we can go back to talking about heaps, heapland. So to refresh your mind on heaps, a heap is a tree that you usually keep in an array, not pointers. And the rule of the heap is that the property of the heap is that if it's a min heap, is that this number has to be smaller than or equal to these numbers. So something like that. Something like that is okay. That's okay as well, all 5s. That's not okay because the 4 is smaller, so that one's bad. Okay? Max heap, on the other hand, is the opposite. So with a max heap, the root node per se has to be greater than or equal to the children. So for example, you have 5 there. That's okay. That's also okay. All 0s, that's okay too. And that's also okay. All right. Cool. So I hope that's a good refresher. So now we talked about inserting into the heap, and the way that you insert the heap is always a complete tree, and you always insert at the next spot in that complete tree. So in this case, we would insert right here. And the way you do that is you first say, suppose we insert let's say we're working with a max heap. We insert the number 10 in there. Nothing happens because it's smaller than the parent. Okay, let's insert 901. In that case, that's bigger than the parent. So you go ahead and you replace them. And you're good. Let's say over here we insert the number 10,000, 10K. In that case, that's bigger than 9,000. So you swap them. And then you go up in the tree. So now you got to check this subtree here. And yet again, you got to replace them. Oh, snap. Failed. That was 9,001, right? Yeah. Or was it 9,001 or 9,000? Check the replay. I don't know which one it was. I forgot. Doesn't matter though. So that's how you insert. How do you delete? Well, you don't just delete stuff randomly. 9,000. Thank you. You don't just delete randomly. You always delete the root value, which is going to be the minimum value in the min heap or the maximum value in the max heap, and then you replace it with the last item in your heap. So let's just do that really fast. So let's say we're working with a max heap. And the reason I'm using max heaps now is because we didn't show them last time. So I don't know what happened there. Okay. So we take out that number, 100, by replacing it with the last item in the list, 8. And then we have to fix the heap property. So this is out of the list now, so marked out. And because this is a max heap, this obviously violates the property there. So you, in this case, because it's max, you pick the biggest of the two and you replace it with that. So in this case, it's the 80. And then you do the same thing on that subtree there. You don't got to worry about the other subtree on the 50, 50, 100 because you didn't modify that. So in this case, again, you pick the biggest number, in this case, the 20, and you replace it with the 8. So I'll just redraw it here. You end up with just that. You can keep the 100 in there, but you don't have to because you removed it. So let's talk about that. When do you keep it and when do you just like flat out delete it? Well, it doesn't matter because when you're implementing this again, if you remember last time I said it's kind of like a stack. You keep an integer point indices to what is the last valid value of the heap. And just like you do in a stack, you don't actually have to like manually erase spot that was popped out of the stack because the moment that you insert something else, it's going to get overwritten. So that's never a problem. So from a implementation point of view, it doesn't matter whether that's there or not, as long as you update that, call it the size pointer, because it's typically, it's a size, which is the same as your index, you know. I mean, it could be off by 1, you know, because if in this case, for example, it would be 0, 1, 2, 3, 4, 5. So it'd be, so this is technically index 0, index 1, index 2, index 3, index 4, index 5. So you have it pointing to, say, the next available spot, which will be 6, but that means 6 is not full. That way your size matches the size. Actually, your index matches the size, but you have it pointing to the last element of the current heap, then it's off by 1. So, you know, it's the same thing if you're using this in a stack. Or if you have like a front and back in your heap and your queues. Okay, so the next thing I want to tell you is how to heapify a heap. So if we talk about time complexity right now, let's not. Let me show you Heapify first, and then we'll talk about time complexity. Yeah. Because otherwise you get a little bit confused. So far, if you remember last class, I showed you Heaposrt. In that version that I showed you, I inserted into the heap one thing at a time, and every time that I inserted something, I have to fix the heap because it might break. So that takes a lot of work. It's a lot of moving around as I'm inserting things, and that's kind of inefficient if your goal is Heaposrt. And so it turns out that there's a faster way of making a heap from existing data, and that faster way takes log n time. To create a heap from existing data. How are we doing on viewers, by the way? See how many people are left. 34 viewers. We haven't lost that much. Cool. So, how does the Heapify algorithm work? I love the name Heapify. It's just like Heapify. But the way it works is, let me just go ahead and put in a couple of numbers. So how about this? Give me numbers. Just spam numbers in chat. 10 numbers. Don't make them too big, please. 88. Okay. I need like 10 numbers. 42, 1, 23, 45, 73, 67. You guys are a good RNG number generator. So we have 2, 4, 6, 8. So that's good. We're good. So, did I make up 83? It was 89. Yeah, that was 89. So that's good. That's enough numbers. Otherwise, we'll be here all day. I think we'll do that much. In fact, I don't like the 1 because it's like 1 digit, and that's going to confuse us. So we'll make it 11. It's still the smallest number. Okay? Now pick. What do you want to make? Max heap or min heap? I'm waiting. Max or min? Max heap. All right. Max heap it is. Oh, man, we had somebody on Discord. I didn't look at Discord. I feel guilty about that. Let's put in the 55 to, because we had a guy on Discord that wrote stuff. So, you know, I can't just ignore him. So, there we go. Okay. So, we're going with the max heap because that was what set for. I'm actually glad because you saw an example of a min heap. So, we can do a big example of max. All right, cool. So, this is in an array. And so, remember the properties of the heap in the array. And for that, I recommend that you check out the binary heap on Geeks for Geeks. There are these three properties that you know two of the three already. I'll post it on chat. There's the way to find from a parent in an array that it represents a binary tree. If you want to find the child indices, we know that it's multiply the parent times 2 and add 1, or add 2, depending if it's left and right. And this is assuming that the array starts from 0. If it starts from 1, then it becomes times 2 and then times 2 plus 1. What you don't know, but now you do, is how to find the parent from a child. And it's just backwards, of which makes sense, of what you have. So to find it, you take the indices of the child, subtract 1 from that, and then divide it by half. And that will give you the parent. As you can see right there. And you're thinking, well, that's not, sometimes that might, like suppose that I'm looking at indice 5, you know, and I want to find the parent of indice 5. You're like, well, actually, no, indice 6. Let's do 6. Because 5 is easy. 5 minus 1 is 4. Divided by 2 is 2. That's okay. But let's say you're doing 6. 6 minus 1 is 5. 5 divided by 2 is like 2.5. So you're like, what's indice 2.5? Well, you got to take either the ceiling or the floor function. In this case, you know, I don't want to lie to you, so let me double check which one it is. So here's the let me draw this for you. Hold on. So it's always going to be one of them, though. I just personally didn't remember which ones, but now I'm going to remember it. This is the way you can remember. Draw the indices like this, and then we know that if from root 2, which is just indice 2, that's what it is. These are the indices locations. We know that 2 times 2 plus 1 is equal to 5, and 2 times 2 plus 2 is equal to 6. So we know how to get from the parent to the child's. I wrote root, but I meant parent. Okay? You can say subtree root as well. The other way around is we're saying take 5 minus 1 divided by 2. 5 minus 1 is 4, divided by 2 is equal to 2. That's good. That is giving us a parent. But when we do it with 6, as we said, 6 minus 1, which is 5, divided by 2, which is 2.5, all we got to take is the floor function in this case. So that's the one. There you go. Not ceiling, floor. But when in doubt in a test, you could do that. That's the way to remember, just like I did right now. Okay? So why am I telling you that? Because the algorithm that I'm about to show you, we're going to work our way from the bottom up. And actually, even when you insert on the heap, you're working your way up fixing the heap, right? And when you're coding this, because you will have to code this, you want to know how to get from the child to the parent. And that's why the array version of this is nicer, because this little math formula here gets you from child to parent. In assignment 6, 7, and 8, when it was all pointers, you have no way of getting from the child to the parent. The only way is to do recursion to the child, and then on the way back, you know where you came from. Or to make it like a doubly linked list style, where like the pointers can go both ways, which is kind of nasty, but perfectly valid. But that's the only way that you could figure out like how to go back and forth. With the array, very easy. You just do that formula, bam, you've landed at the parent. That's why heaps are much nicer done on arrays. And in general, trees are so much nicer here because it's easy to access anywhere in the tree. I'm sure that you guys could develop a formula of how to get all the grandchildren nodes. Oh, this is a good test question. Now it's not anymore, but maybe I'll ask it next semester. I'll have to remember. This would have been a cool test question. Think about it. Okay, pop quiz right now. This is the test. Test 2, you know, you're sweating. You see this question on the test. I'm going to put it in here. How or create a formula to compute all grandchildren nodes of a given node. That would have been a beautiful question to put in a test, actually. Like, if I don't forget it, I'm going to ask next semester if I teach 302, which I think I will. So don't tell your friends, or if you do, they won't believe you anyways. So that's okay. But yeah, that's a cool question. So what's the answer to this? It's an easy question, actually. I mean, think about it. So you put x well, we're saying to find the grandchildren, not to find the grandparent nodes. So in that case, the solution to this is, I got to think about it. I don't know the answer actually on the top of my head, but I think I have an idea. If 2 times 2, or sorry, if x times 2, and we're saying grandchildren, so we're not including the parents, or in this case, the children, which are the parents of the grandchildren, right? So by the way, I guess I should draw this. What we're trying to do is we're trying to find the address of these 4. So how do we do that? Well, let's number them A, B, C, and D. What's A's formula? It's going to be, and this is our x, it's going to be x times 2 plus 1 would give us this guy here. And then we take that and we kind of recursively do this by saying times 2 plus 1. B is going to be the same thing, plus 2. What's C? See if you guys had it right. So you guys were x minus 2. There's no minusing because, again, that would be if we're going upwards, which we can do next. X times 2 plus 1, x times 2 plus 2 twice. 4x minus 2 left. Well, let me simplify it because maybe you simplified it already. Oh, that's early for that math. 2x plus 2 plus 1, 2x plus 3. So this is 2x plus 3, which you had 4x plus 3. Well, the other one might have been that. The other two are going to be x times 2 plus 2 times 2 plus 1, and then D would be x times 2 plus wait. Yeah, 2 times 2 plus 2. There we go. So whatever, you simplify that, and I did a mistake. It's 4 times. Did I? Oh, yeah. My bad. Right here. Yep. Right here. So 4x plus 3. So yeah, you had it right. You had at least that one right, and then the other ones you can simplify on your own. But yeah, that would have been a cool test question, and it's not hard. It's if you conceptually understand how the children relationship work, right? And then the other way around is just it's almost like doing recursion by hand. So would you guys have gotten this on the test if it was a question in midterm 2? And how long would it have taken you? You know, it smells like fear. I don't know. Maybe that's just me. Yeah, it looks like you're plugging in equations. You are essentially just plugging in equations. Anyways, we're getting too excited with that. But yeah, so that's the kind of question you can expect on a test. Well, this formula applies for anything. For any binary tree, technically. So, you could repeat the same thing to find, you can create a recurrence relation for this, technically. So, anyways, where were we before that? Okay, we had a list of numbers here. Oh, snap. Oh, I don't know how that opened up in the random email. That's a strategy I have to try. That's good. Okay, so the Heapify algorithm is going to take numbers, throw them on the heap, or at least a representation of a heap, and then turn it into a heap. So we have the numbers that you guys were kind enough to give me, and now we're going to build a tree out of that, just as if what you gave me was a level order traversal of such tree. Tell me if I make a mistake copying these down here. There we go. Okay, so we got a nice little binary tree. It's not a heap at this point. It's not even a binary search tree. It's just a binary tree. Okay, so we are going to heapify. And yes, you would get this asked on a test to heapify that. So how do you do that? Well, you work your way from the bottom up. Even though when you're coding this, you can code it from the top to bottom, which is weird, but you could, yeah. It gets kind of messy, which is why it's taking me a while to get the assignment 9 out. But yeah, okay. So you're going to do this from the bottom up, and essentially what you're going to do is you're going to heapify the subtrees, which will then heapify the bigger trees, which will then end up in the final tree. So this is actually, if you remember Zelda, which I actually never played a game, but I know Zelda. Remember the Triforce logo? That's what you're trying to achieve. And if I had time, I would have changed the background to Zelda right now. But you know, I can just draw myself a logo here. There we go. Background. So out of all the stuff you play, that's the one you miss. Whatever. It's just Zelda. I mean, I play Zelda in Smash. You guys saw that. So anyways, the Heapify algorithm is like trying to make the Triforce logo. That's the goal. I'll put it to the side here. Okay. So what we're trying to achieve, what color is the Triforce logo? Like orange? I don't know. Is we're going to heapify this subtree, and then we're going to heapify this subtree, and then this subtree, which will then allow us to heapify this subtree, which, as you can see here, is our little Triforce logo if we drawn it nicely. He meant Link, huh? No, I played Zelda on Smash. So anyways, okay, we're doing, you guys wanted a max heap, right? So, and we're almost at the 1 hour 15. So if you guys, I mean, I don't know, if you guys can hang out for a little bit, we'll get to the max heap here. So what we're gonna do is we're gonna start from the bottom and we're gonna work our way up. So in this case, we're gonna heapify that subtree here. And because it's max heap, we're going to pick the biggest of those three numbers and we're going to make it the parent. And that's it. We're good. So in this case, 89 is the biggest one. So we're going to swap 89 with 23. And now this is part of our little Triforce. So we'll color it. Okay. Next, we're going to do the same thing on the next tree that's available. And by that, I mean, there's nothing that we haven't done beneath it. So technically, we have two options here. We could do this one, or we could do this one. So let's go ahead and do let's just do the 1173-67 one. Why not? So in that case, 73 is the biggest one of them. So we're going to put that as a parent. And now we have heapified that one. Okay, next, we'll do this one. This one, the biggest one is 89. So yet again, that's kind of bubbling itself up. here's the thing though. When you do that bubbling right there, it's possible that things beneath it may have broken. As the case has happened here. Look at that. And I didn't plan this. You guys gave me the numbers. 42 right there is no longer correct. It's no longer the max heap right there of that subtree. Because 55 is bigger, right? So whenever you change something in the bigger scheme of things per se, in the bigger tree, you need to go back down and make sure they didn't break things beneath it. So in this case, it did. And we have to swap the biggest one again. So 55 and 42 have to swap. Does that make sense? Because that's, I guess, the trickiest part of the algorithm. You're working your way from the bottom up. But whenever you swap something, you got to check the children of what you swapped to see that it didn't change anything. If 45 had children beneath it, we wouldn't need to check that because 45 never moved, I think. The one that moved was 55. And when that moved, it changed things beneath it. So, same with these, which are, I think, with the 67. The 67 we didn't touch. So, because technically, if we're doing that part, it means that we've done anything beneath it. That's okay. So anyways, that's okay now. So we can move on to make the bigger triangle, which is this one. So that one, the biggest one is the 89. So that's going to become the new parent. And so here's the thing. We didn't touch this subtree, right? Therefore, we don't need to verify it. However, we did touch this one and anything beneath it. So we do need to check that. And in this case, nothing got changed in this one right here. I mean, like the 88 is still the biggest number. So that's okay. At that point, we can stop. We don't need to check that one down here. We don't need to check this one. Because nothing got changed up here. You could, and then you'd see that nothing would change. This is like bubble sort. When you have the flag to that you say nothing got swapped and you stop the algorithm. Same thing here. If nothing got swapped, then you don't need to keep going down. It's only if something did get swapped. The efficiency thing. And there we go. At this point, we have finished the little Triforce thing, and it is a max heap. We have heapified this. How long does this take? Well, I have here from Heapsrt. So on Geeks for Geeks, there's a binary heap section and there's a Heapsrt section. As I said, heapifying takes log n time. And then to create and build a heap, it takes n time. However, the reason why Heapsrt, I don't agree with this actually. The reason why Heapsrt takes n log n time is because once you have heapified the algorithm, you got to take out one number at a time to, as we did last time, to get it correctly. And so that's where it's getting that. And then you have to reheapify things afterwards, which will take n log n time. So that's where n log n comes from. So, how do we feel about heaps in general? Do we understand them? Do we understand Heapify algorithm? At this point, we're hitting exactly 1 hour 15. Pretty well. So, you have to Heapify doing Heapsrt. So, you could do it the way that I did before, which was to insert thing one at a time. But that takes longer time. It's not as efficient. You want to do it this way. You want to heapify your data first and then pull out one at a time because heapifying is faster. And yes, you want to heapify because you want to build a heap before you can extract. Because what is a heap going to do? It's going to generate a tree where the root is the smallest number. So you can write more questions if you have them. But let me talk very briefly about the homework. So, one of the uses of heaps is to create a priority queue. What is a priority queue? A priority queue is just a queue that has the ability to have priority between people that are waiting in the queue. So it's like you have people waiting at the DMB, but then you also have, say, different tiers of importance. So like maybe they know that the people that are just doing renewals of something are faster, so they give them more priority. Or maybe there's a VIP lane, or the handicap lane, or the fast pass in Disneyland. So one of the ways that you can do that is you can do the circular queue thing that we did as assignment. What was it, like 4, I think, or 2? I don't know which one it was. You can do that, but it's kind of nasty to keep track of that. The other thing you can do is you can use a heap. Yeah, assignment 4, right? You can use a heap because, like, suppose that we were doing a min heap or a max heap. It doesn't really matter, but let's say max heap. The bigger the number, the more valuable of a person that you are, and in that sense, you can cut the line. So you start with a bunch of numbers. These are all people that wanna be served at the DMB or at the Disneyland ride or whatever, and then you give you give a key to each of them, which is the numbers that we have here, that represents how important they are. The bigger the number, the better the higher priority. If you don't have any sort of priority, then you can just all give them the same number, and when they get put in the queue, then they're going to be all over the place, right? So you could maybe order them by like saying first person gets number 1, second person gets number 2, but then we can also create a second number 1 value, so that they can go first. So like for example, suppose that we have 3 people in line. He has ticket 1, ticket 2, ticket 3, or maybe 4. And then suppose that somebody comes in who knows people there, and they just give him another ticket 2. So in that case, this guy, because he has another ticket 2, is going to go before these 2 guys. He's going to kind of cut them. He's still not as important as this person, but he's the same level as this one. So that's a usage of a heap. You can when you create a heap and you're removing numbers. So like if this was to be on a heap, let's say it was a min heap now, this would look like this. There we go. And so when we remove this one here, this would get replaced with a 4. And then the heap property would throw it down first here and then here, and you'd end up with this. And then the 2 would come out. And then from there, you've replaced it with a 4 again. And then you fix the heap, which would end up like this. Hold on, I lost track of myself. There we go. You took one of the 2s out, so you still have the other one left, I guess. There we go. And then you take that second 2 out, which gets replaced with the 3. And in that case, it's already a heap. Then you take the 3 out, which gets replaced with a 4. And then you take the 4 out and you're done. So that's a priority queue, because at any time with the remaining numbers, I could have thrown in another 2 in there or even a 1. And they would be the next person to be served. So assignment 9, you will be building a priority queue that represents the order that ships have to leave from Heathrow's forward operating base to fight the invading force in Normandy. Which, don't worry, we'll get the whole theme going in the assignment. Okay. So we have a question. For assignment 8, with everything we got on assignment 5, what do we have to keep? All you really need to keep is the concept of the system class Star Destroyer objects. And then you got to put these objects inside your binary tree, search tree, which is an Avl tree. And then you need to print them out in the in-order traversal. So you don't need to keep the linked list vector or anything like that in it, or any of the sorting algorithms either. No, you don't. You just leave it in there, but you don't make it run, because otherwise it'll take too long to run, I think. With the command line checks, you don't have to keep any of the command line check stuff, or you can add a new command line argument for the Avl stuff if you want to. I mean, if I was you, I would like make everything work together and then just make it an option with the command line arguments, because then at the end of the class, you'll have a big project that you're like, look, I did all these data structures. It's a really huge project. There's like 10,000 lines of code or something, and then you can be happy about it. Don't post it on GitHub or something, but be happy about it. Yeah, pretty much. I mean, you still want to have the objects. Don't make them objects. Don't make them just like text. They're still system class star destroyer objects. Okay, so back to the schedule of things that we did. We talked about Heapify, max heap, priority queues. The homework, like I said, is you have to build a heap. And so I'll get that done pretty soon. And then we'll, I'll give you time to do it afterwards. And we also talked about Avl delete. And we also talked about stable heap sort. We didn't get to talk about binomial heaps, which is not part of the course. I wanted to talk about it. I'll do like a 2-minute intro to them, and then you'll talk about them when you get to analysis of algorithms. And we also didn't talk about tries either. So I will talk about this some other time. But binomial heaps is a way of keeping multiple heaps together. So like each heap, so like suppose you have 2 priority queues and you want to merge them together for like a massive weight. So like suppose that you have 2 DMBs that are running, and then one of them has to shut down, and you gotta combine that queue with the existing one, something like that. That's one way that you can achieve this, is using a binomial heap. And a binomial heap is the collection of heaps, and it's a little bit tricky how you merge them together, but essentially you have sort of the top layer, which contains a pointer to the root of each heap, and you sort of point them together as well, as you see here. In fact, video is good for this. Oh, I hope that wasn't loud for you guys. That was loud for me. So here we have a bunch of heaps. Here we go. Here we have a heap. This is the 6 is a heap. The 3 is also a heap. This is a heap. That's a heap. That's a heap, and that's a heap. These are all heaps on the top level. They have other stuff in them, but they're heaps essentially. And the way it works is to combine them. You can either combine the heaps by making them child of previous heaps, but you can also keep them separate. But so that they don't grow into like an infinite amount of heaps, you can only keep one heap of each order. Meaning that if this heap has only one level per se, or one child, or no children, you can only keep one type of that heap. Just like you can only keep one type of heap that only has one child. And then you can also keep only one type of heap that has 2 childs. And as you can see here, within this level, you can have more than a binary heap. This is now, we're talking of no longer just a binary tree. We're talking about more than just binary. It could be any degree. And so how do you merge them together? You go ahead and you first sort of sort them by order. So like these are individual node heaps. These are pairs of heaps. So this tree is going to move over here. Okay? And once you finish sorting them, wait, went a little too far. Then you're going to combine heaps that are of the same order per se. So like these 2 are the same order and these 2 are the same order. And the way you combine them is you just make one the child of the other one. So in this case, you'll see that the 12 becomes a child of 18 because it's a main heap. And then you're going to do the same thing between this one and this one and this one. So this one's actually going to become the child of 3 right here. You'll see that in a second. And you keep a previous, a current, and a next pointer to deal with this, to traverse all the way. Come on. There you go. It got merged into that. And now yet again, these 2 are the same order per se. And so this one's going to become the child of that one. Or actually, no, this one's going to become the child of that one because this number is bigger than that one. And there you go. Again, why? Because 3 is a min heap. It's smaller than 15. So that's why this one's the one that became the child and not this one. And now you have 3 heaps, but you don't need to combine them anymore because they're all of different orders. And you're good. And I think that's the end of the example. So this is just what's in your future once you take analysis of algorithms. But we don't get to talk about that. We don't get to talk about Fibonacci heaps because just talking about a heap in general is enough. And so in the test, I'll ask you about binary heaps. I won't ask you about these guys. Okay, so that concludes the lesson. Again, tries is just a subject that I'll throw in there. But essentially, other than tries, we're practically done talking about trees. From now on, we're going to talk about hashes, and then we're going to talk about graphs. Now, yes, a tree is a form of a graph, of a directional acyclic graph. But yeah, we're done with trees now. Tries is a tree also, but that's optional subject, which I'll throw in. Worst case scenario, I can make a for fun video on them. And they're actually kind of useful. I use them for that Wikipedia project, actually. Between me and Ben, we were using them. But yeah. So, oh, could you please send a Discord link? No, I'm not going to send a Discord link because we had random people join last time and that was sketchy. So you can go to Canvas to get Discord. Okay. So, if you want, yes, if you want the Discord link, you can go to Canvas or send me a direct message via Canvas. Let's see. If there are no more questions, then that's the end of the lecture, by the way. For me, it was easier to add the Avl stuff than delete the old stuff. Yeah, blah, blah, blah. I'm looking forward to hashes. Yeah, so am I. Okay. All right, then. Well, I will be on Discord if you guys have questions for a while. And for future lectures, before next week, I'm going to check the polls and see if there's a better time that we can do them. And then we will also, I'll figure out what's the deal between using YouTube or Twitch. But now I have at least both of them. So if one fails, we'll just switch to the other one. So always just keep track on Discord for the latest news in terms of where's it going to be hosted at. I think most people prefer YouTube, but this has less delay, which I like. But now I have to actually upload the video to YouTube. So we'll see. But all right then. Enjoy your weekend. Stay updated. I will post the assignment once it gets done. And get that Avl trees done. Get them balanced. All right then. See you all.